Hello, I wanted to look at with you some of my thoughts on this reactivity trends demonstration. Hopefully you've had the time to think about this yourself, share with your colleagues, and get their feedback. And here we go. So if you remember, what did we do? Oh yeah, we put sodium, lithium, potassium in water. I think we might have also put magnesium and calcium in water, looking for the trends and reactivities. Those are the questions. Hopefully you're familiar with them by now. The first one was, draw and label a cartoon illustrating why, emphasis on why, rubidium is more reactive than sodium. Excuse me, sorry about that. The cartoon I drew is very simple. I have a large sphere, gray as if most metals are grayish or silver, representing a rubidium atom, and a smaller one representing a sodium atom. How would you know 186, 247? You wouldn't unless you looked them up, but hopefully you know the trend is the lower down on the table you go, the larger the atom. So if indeed rubidium is a larger atom than sodium, and even though they're both in the first family, and they both have one valence electron, which makes them both pretty reactive, rubidium is more reactive. Let's see, oh yes, isn't a 5s1 electron further from the nucleus than a 3s1 electron? And why would we care how far they are from the nucleus? Oh yeah, isn't it the positive nucleus that attracts the negative electron? And the further the electron is from the nucleus, the less strongly held it is by the nucleus, even though rubidium does have more positives in the nucleus than sodium has. You might think that, oh geez, what is it? Where's my periodic table? I don't even have my glasses on. Let me look. Oh, how embarrassing. 37 pluses. Rubidium has 37 pluses and 37 negative electrons buzzing around it. Buzzing around, bad model. But in any case, the story goes like this. Since rubidium is larger, more layers of electrons, its single valence electron is further from the nucleus, and the electrostatic attraction between the nucleus and the outer electron is less. Also because rubidium has more nuclear shielding. Those 37 positive charges in the nucleus, the protons, are shielded from being able to attract that 5s1 electron of rubidium by 36 other electrons existing in stable configurations, stable orbitals I should say, between here and here. So it's mostly empty space, but there's a whole bunch of 36 electrons like that getting in the way of 37 positives attracting that single negative, and that single negative 5s1 electron is quite a ways from the nucleus relative to the 3s1 electron of sodium. So anyways, the bottom line is, number one, because the electron is further from the nucleus, because it's a larger atom, and also because, number two, there's more shielding getting in the way. What would we say the shielding looks like here? 11 pluses and 10 negative electrons between here and here do interfere, but not as greatly, do interfere with the attraction of the positive nucleus with the negative electron, the 3s1 electron. But those other 6, 7, 8, 9, 10 electrons don't shield as much as those 36 electrons. 6 and 10 and 2 and 6 and 2 and 6 and 2 and 2 add up to 36, and there's the 37th electron there. Anyways, think about it. What I concluded, both sodium and rubidium have very reactive, as they lose their single valence electron pretty easily, but the 5s1 electron of rubidium is even more loosely held, and therefore, if that electron is more loosely held, that type of atom, that element as a macroscopic sample, is more reactive. So I bet you were able to look up the equations, but it's good to think about them. Lithium in water, hydrogen gas. Sodium in water, hydrogen gas. Potassium in water, hydrogen gas. Lithium, sodium, potassium, rubidium, cesium all would react the same way. Calcium, metal, in water, hydrogen gas. Barium, metal, in water, hydrogen gas. So these metals don't dissolve in the water. I like to say they react with the water, enter into a chemical reaction bonds breaking and bonds forming, breaking old bonds, forming new bonds. Of course, you see the strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide. The OH minus ion, the hydroxide, strong base. You might want to start remembering that for the future. Cartoons, lithium ions. Oh, the balanced equation said 2 lithium atoms and 2 waters. 2 lithium atoms and 2 waters react to give 2 lithium ions, 2 hydroxides, and a hydrogen gas molecule. That's 1 hydrogen gas molecule, 2 lithiums and 2 hydroxides. These are all floating around in the water because, well, for one thing, lithium hydroxide is able to dissolve in the water. We're forgetting about all the waters involved. There are actually lots of waters surrounding these lithium ions and the hydroxide ions. And there'd be, if I took a 1 gram or even a tenth of a gram sample of lithium, there'd be millions and millions and millions of these sodium ions and hydroxide ions and lots of hydrogen gaseous molecules evolving off. Sodium's a little bit larger of an atom than lithium, so I do its sphere a little bit larger. Sodium ions are also therefore a little bit larger than the lithium ions, but the sodium ions are smaller than the sodium atoms they came from. Interesting. So there's a lot of similarities between this cartoon and this cartoon, but a couple of important differences as well. Sodium ion being larger than the lithium ion, sodium atom being larger than the lithium atom, lithium ion being smaller than the lithium ion atom, sodium ion being smaller than the sodium atom, and calcium's a larger atom even still. The balanced equation said 1 calcium and 2 waters. That's how I read that or interpret that if I'm thinking about this on a molecular scale or molecular ionic scale. Yeah, all right. Well, feel free to ask me or a TA or a learning assistant about questions you might have about that, because right now I'm just talking to a stupid old computer in my own boring office. No, I'm having fun. I'm kidding. Really, I am. Because I'm a chemistry nerd. I like science. Why, on fundamental physical and chemical principles, is the trend in reactivity for the halogens, fluorine, chlorine, bromine, iodine, opposite the trend in alkali metal activity? By that we mean, you remember, as I go from lithium to sodium to potassium, we've already explained why potassium is even more reactive than sodium, which is more reactive than lithium. And when rubidium and cesium will be even more reactive than that, because we know they like to give up their electrons, and the further from the nucleus those valence electrons become, the more overall reactive that first family alkali metal is. So why is it that fluorine, chlorine, bromine, and iodine are even, the trend is opposite? So by that I mean fluorine is more reactive than chlorine, and chlorine is more reactive than bromine, and bromine is more reactive than iodine. What did I say here? For one thing, these are nonmetals, and nonmetals don't want to lose electrons. Nonmetals want to gain electrons. So the question then is, why does fluorine gain electrons more vigorously, more exothermically in a sense, than the chlorine atoms? And the answer is something to do with, again, positive and negative attraction. So if instead of trying to lose electrons, I'm gaining electrons, what makes fluorine, or maybe I should say the nucleus of the fluorine atom, more able to attract electrons, or more strongly attracting the electrons than the chlorine? In a sense, we've already answered the question. Which is the smallest atom? Which nucleus of which atom can get in the closest proximity to the electrons and try to attract them with the most strength? Well, you can already read it. It's right there in front of you. You know the answer. It's the fluorine nucleus. Even though it has fewer protons, is able to, than chlorine and bromine, it is able to get closer to the potentially attracted electrons it's trying to gain. And because it can get closer to them, it's a smaller atom and there's less shielding. Because it can get closer to those electrons, it can attract them more vigorously. And if it can attract them more vigorously, it releases more energy, called electron affinity. It releases, electron affinity. Think about that for a second. So if a fluorine atom gains an electron, it releases a whole bunch of energy. If a chlorine atom gains an electron, it releases energy, but not as much. If a bromine atom gains an electron, it releases energy, but not nearly as much. Perhaps that's because these, oh geez, what is it? Oh, for here it'd be five. No, here it'd be just be shielding four inner core electrons. 1, 2, 3, 4 shielding. Here we have 6, 7, 8, 9, 10, 11, 12. Yeah, no, 6, 7, 8. Yeah, I guess it is 12. In a sense, 12 electrons. That's debatable, but there's more electrons here on the inner core and more electrons here on the inner core. And as you have more electrons on the inner core, they shield that nuclear charge and don't let those nuclei, that nucleus, positive charge, attract passing, neighboring, negative electrons that they might encounter. Am I just rambling to myself? Does that make any sense at all? If not, feel free to ask in lecture, in discussion, in private, office hours, whatever. You gotta ask. If you don't ask, you're never gonna make sense of it all. Maybe make sense already. In any case, thanks for watching, and I'll see you soon.